In today's video, we're going to be moving on to the second component of how to evaluate an NMR spectrum, and that's a chemical shift rationale for how to explain each one of these peaks. Now, just as a recap, we said that chemical shift was talking about this x-axis and where the peaks fell on the x-axis, and these numbers are going to give us information about functional groups or functional group generalities that hydrogens are going to be attached to. So all of this information that we're getting is all hydrogen centric, and it's going to give us information about the general arena or area that these hydrogens are going to be attached to. And just to make this discussion a little bit more practical, what I've done is I've included a pictorial graph of the generalized regions in a ppm scale of where hydrogen peaks can fall. And if a hydrogen peak might fall in a general region like this kind of reddish region, what type of functional group or what type of atom those hydrogens are usually going to be attached to. Now, this is not a catch-all graph. There are some exceptions, and we're going to talk about those exceptions a little bit later. But just to get going, let's talk about this graph in a general sense very quickly. So what you'll see is I've subdivided this graph in about 6 separate segments, and these are the traditional segments that you'll see whenever you take an organic chemistry course. So just kind of going really far left to really far right, let's talk about the types of atoms or functional groups that hydrogens are going to be attached to and about where they'll fall on the ppm axis. So on the very far left, somewhere between 9 and 11 ppm, you're normally going to find hydrogens that are attached to either carboxylic acids or aldehydes. So these hydrogens are going to either be attached to an oxygen for the carboxylic acid, or they're going to be attached to this sp2 hybridized carbon right here. So in general, these are the functional groups. These are usually the only two functional groups that show up this far to the left. Again, there are always exceptions, so don't take this as a hard and fast rule, but it is a generality. Okay, next region, you're going to find hydrogens in this region somewhere between 6.5 and 8 ppm if they're attached to benzene rings. So this hydrogen right here is going to be attached to this carbon that's sp2 hybridized, but specifically, these types of hydrogens that are attached to sp2 carbons are going to be benzene in nature. Now you'll notice that if we go a little bit further to the right from 4.5 to 6.5, this is a very similar scenario where you have a hydrogen still attached to an sp2 hybridized carbon, but its general region for where that peak is going to show up is a little bit further to the right. So again, sp2, sp2, but the main structural differentiation here is that you've got a benzene ring. Now there will be other structures other than benzene that show up in this region that are going to be aromatic, but again, this is kind of the catch-all functional group that you'll see if you're talking about this type of region. So again, this is the aromatic region, and if you're in organic chemistry too, your professor at some point in the near future will probably be talking about aromatic molecules, but this is going to be that region if you have an aromatic molecule. This next region just to the right, we refer to this type of hydrogen that's attached directly to an sp2 hybridized carbon. This is what's called a vinylic hydrogen. And so if you have this vinylic hydrogen that's not attached to a benzene, this is the general region where you're going to find these peaks. Okay, next up, just to the right of that, 2,5 to 4,5. You're going to find peaks in this region if you have hydrogens that are attached to sp3 carbons, like this guy right here, but that sp3 carbon is then attached to an X. Now, what's the X? The X could be a lot of different things, but in general, we think of this X as being either an oxygen, nitrogen, or a halogen. So this could be a chlorine, bromine, fluorine, whatever, but if that hydrogen is attached to the carbon, and that carbon is attached to an X, you'll generally find peaks in this region. And another way that we can think about this relationship between the hydrogen and the X is that this hydrogen to the X, there are 2 bonds in between these 2 atoms. So if you have this type of relationship where you have 2 bonds that separate 2 atoms, we actually have a special term for this. These 2 atoms, if they're 2 bonds away, are going to be referred to as geminal atoms. And so if you have an H that's geminal to an X, if X is oxygen, nitrogen, or a halogen, you're generally going to have a peak in this generalized region from 2,5 to 4,5. Okay, so moving on a little bit further to the right, the next example, we can actually have 2 different types of structures going on that'll give us peaks in this region from about 1,4, 1,5 to 2,5, somewhere in this region. And if you look at this bottom structure, it actually looks very similar in the way that it's drawn to this vinylic sp2 hybridized carbon. So what you'll see is that in this example, you still have this sp2 hybridized carbon, but if we're talking about hydrogens, this is the hydrogen that would give us a peak in this region. This hydrogen is actually attached to an sp3 hybridized carbon. And if this sp3 hybridized carbon is attached to an sp2 hybridized carbon, so right over here, sp2, we can actually give a name for this type of relationship as well. So these type of hydrogens that are attached to the sp3, and then that sp3 is attached to another alkene sp2 carbon, this type of hydrogen is going to be called an allylic hydrogen. That's the term for it. And if you have allylic hydrogens, they're going to be definitely different than vinylic hydrogens. These guys are going to show up much further to the right. Okay, so in the other structure that I've drawn up here, we kind of have the same thing, but not really. So for the top structure, if you look at the hydrogen, it's also attached to an sp3 hybridized carbon, and then we have this other carbon that sp3 is bound to. This guy's also sp2. So this carbon is sp2, this carbon's sp3, looks very similar to the example down below. So what we would call this hydrogen is, you could either refer to it as an allylic hydrogen, or if you want to be a little bit more specific, you could say that this hydrogen is alpha to a carbonyl. So that's another way to think about it. This hydrogen is alpha to a carbonyl, where this is the alpha carbon. So either way, potato, potato, you could refer to this as allylic, and if you called this an allylic hydrogen, and if you drew the structure, people would know what you're talking about. But if you wanted to say this is an allylic and you wanted to be really specific, just to make sure that people knew that there was an oxygen, you could say that this hydrogen was alpha to the carbonyl, because this is a carbonyl and that's not a carbonyl. So just to give you some tools. Okay, so you have two options here, and both of these examples are going to show up in the same generalized region. And then finally, all the way to the right, we have the most boring structure that you could potentially have, which is just an sp3 hybridized carbon that's got nothing attached to it other than a hydrogen. So this is what's called the saturated region. So this is the saturated region, and this generally shows up somewhere between 0 to 1 to 1.5, somewhere in there. So if you have a hydrogen and it's just attached to that sp3 hybridized carbon and there's nothing else around it, there's no geminal to an oxygen, nitrogen, or anything like that, these guys are going to show up in that 0 to 1.2 or 3 or 4-ish region. Okay, just a little bit more terminology. When we're talking about chemical shifts, a lot of the times you'll see two different terms thrown out that generally confuse people at first glance. And these two terms are downfield and upfield. And the only thing these two terms are used for is just to describe where peaks are found on the x-axis relative to other peaks. So let's just say if we were talking about these aromatic hydrogens, we would say that these are located a little bit more upfield than these carboxylic acid or aldehyde hydrogens. This region is a little bit more downfield. So whenever you're thinking about something going downfield, you should think of peaks kind of migrating from right to left. And if you're thinking about peaks kind of showing up a little bit upfield, you should think of them going from left to right. So this is a bit counterintuitive, because when you say up, you think numbers going up, but really what upfield is saying is if peaks are going in an upfield direction, the numbers are actually going down. It's super confusing, I understand. So just keep this in mind whenever you're talking about terminology. You're using terminology for upfield and downfield. Upfield is to the right, downfield is to the left.